Yes, thank you. So because Michael just explained what maps are, I'll still give the definition again so that we are all on the same page. What I'm looking to today is planar maps, which is the embedding on the sphere of a planar graph connected and considered up to homeomorphisms, which means that I allow continuous deformation. So this map on the left, which is a house with a chimney, is exactly the same as this moon with a nightcap. On the other hand, these two maps are not the same. It's not a continuous deformation to cross an edge. So a planar map and a planar graph are different. The notion of planar map encompasses the cyclic order around a vertex. So all my planar maps will be rooted, which means that I distinguished an oriented edge, which I draw by a little arrow, just like this. The size of a map is its number of edges. And contrary to graphs, we have a notion of corner, which is exactly what you imagine a corner to be. It's the space between two edges. And notice that I have drawn my maps on the plane. It's the same thing as drawing them on the sphere by stereographical projection. And what I'll be talking about specifically is tree-rooted maps, which are planar maps endowed with a cover with a spanning tree. These two tree-rooted maps are not the same because even though there is the same underlying map, they do not have the same spanning tree that I have distinguished in green here. Why are we looking at that? Why am I bothering you with this topic? Because decorated maps are in fact really interesting from a physical point of view. When we have a map without decoration, we are in what can be called a pure gravity case. So we have a field, but nothing is interacting in this field. So it's quite limited as to the behaviors that can happen. On the contrary, when adding a decoration, now we have matter interacting in our field. So results from theoretical physics predict that there will be interesting behaviors in this case. And the goal of the work here was to find such a new behavior and to study it and understand what can happen that we don't already know of in the realm of maps. The tree-rooted maps are the kind of decorated maps we are focusing on today because it's a very well-known model. So there are already interesting results that we can build on, especially with the combinatorics of tree-rooted maps is well understood through Mullin's bijection, which showed in particular that the number of maps of size n is Catalan n times Catalan n plus 1. Unfortunately, on the other hand, the geometry of tree-rooted maps is not well understood for the moment. And what I want to do, as I just said, is to show new behaviors for this kind of maps. That's why we will that's why we exhibit a phase transition in tree-rooted maps. And for that, we use block-weighted tree-rooted maps. And this block-weighted thing is what I will explain just now by going in the realm of non-tree-rooted maps first. So as was discussed by Michael just before, we have universality results for planar maps. So we know how the number of planar maps of size n behave when n's tend to infinity, and we have the following of asymptotics. We know that if we take a uniform map of size n and two uniform vertices, the distance between these two vertices is around n to the power of 1/4, and we have a notion of limit that is not important really for our talk. Just admit that if you do not know what this is, just admit that this is the notion of limit for maps, which is what we call the Brownian sphere or the Brownian map for general planar maps. And what's even more interesting is that these results are true not only for the class of general maps, but for a lot of classes of natural classes of maps. So we have the same formula for enumeration. The constant kappa and rho are not the same, but we have the same shape, and there is the same scaling limit. On the other hand, we have another very well-known class with such universality results, which is plane trees. The enumeration this time has exponent n to the power of -3/2. The distance between two uniform vertices is square root of n, and the scaling limit is what we call the Brownian tree. And once again, there is a universality phenomenon. So we have the same shape for the asymptotics of the map of the enumeration and the same scaling limit for natural classes of tree, but also for some classes of maps, such as outer planar maps or maps with a very large boundary. And that's really interesting and poses a question: is there an interpolating model between these two rich, interesting situations? This question is natural, maybe from a mathematical point of view, but also from a physical point of view. And in fact, it was introduced by Bonhomme in 2016 in the context of statistical physics. And the tool we'll be using for this interpolation is block weighing. So what a block is, in fact, a two connected component. So you might be familiar with connectedness for graphs, which means that we need to remove at least one vertex to disconnect. When two connectedness is when two vertices must be removed for disconnection. And a block will be a two connected component maximal for inclusion. So here, for example, is a map decomposed into blocks. Decomposition of in blocks of maps has been already quite studied. It has been shown that there is what one calls a condensation phenomenon, which means that for a large random map, you will find a macroscopic block, and all the other blocks will be much smaller. On the other hand, for trees, the situation is quite trivial. Each edge is its own block. That's what gives the intuition that block might be an interesting way to do the interpolation. The model we'll be looking at in particular is using a Boltzmann, what is called a Boltzmann weight for blocks. So we use a variable u, and we choose that the map M of size n is drawn with probability proportional to u to the power of its number of blocks. So when u equals 1, it's simply the uniform law on maps of size n. When u tends to 0, maps with very few blocks, such as two connected maps, will be favored. And on the contrary, when u tends to infinity, maps with a lot of blocks, for example, trees, will be favored. And the question we answer is, given u, what is the asymptotic behavior of M drawn according to P and U when n tends to infinity? I've done a few simulations to show you what such maps look like. So this is for u equals 1. So it's a uniform map. U equals 8/5, u equals 9/5, u equals 5/2, and u equals 5. We should not overinterpret these simulations, obviously, but at least it does not seem too strange to, I mean, it's not too far-fetched to say that indeed when u increases, the map looks more like a tree. And we'll show that formally, and the tool that we'll use for that is block tree. I've not mentioned it before, but this is based on a joint work with William Flora from UNSW. The notion of block tree is inspired from Tutt's work in the 60s, who tells us that, in fact, a map can be obtained simply from looking at the block containing its root and then taking notes on what we find in each corner of this block. So let me explain this on an example. Here we take the block containing the root, and then we have a canonical order that we choose for the corners. we write down what we find in each corner. So in the first corner, we find nothing. That's why we write this small black square. In the second corner, we find this yellow map. Third corner, this red map. Fourth, fifth, sixth, seventh, this purple map. Eighth, ninth, 10th. And in fact, since the order on the corner is fixed, all the information we have on the right is sufficient to get back at the map we had on the left. So this amounts to an equality on a generating series, which can be read this way. A map is simply a block where each corner is endowed with another map. And since each edge has two corners, it means that each edge is endowed with two maps. And those maps are potentially empty. And this can be written with having a weight U on blocks. And this gives the following equation for the generating series. This term 1 minus U is simply because we want that the vertex map, which is technically two connected, is not counted as a block. And this, this is all the more interesting that we get that there is an underlying tree structure, because we can do exactly the same with all those three triangle maps here. This underlying tree structure was made explicit by Luigi Adariu-Berry. And let me finish it on this example. So for the yellow map, the block containing the root is a whole map, so there is nothing more to see in the corners. So we'll just write black squares everywhere. For the red map, it's more interesting. We have the block containing the root, which is simply one edge. And then in the second corner, there is this pink map on which we can iterate again this procedure, 1, 2, 1, 2, etc. And this on the right is what we call the tree of block for the map on the left. This block tree has a lot of very interesting properties. So the most important one is that it's in one-to-one correspondence with maps. So the map is entirely determined by the tree with its decorations on the internal nodes. And even if we forget the decorations, we still have information because the number of children of a node is twice the size of the block, which is a decoration. Here, for example, you have 4 children. It's a block of size 2. So just looking at a tree, non-decorated, we still get information on the block sizes. So it's a really useful tool. And it's even more useful that we know how to characterize its probability law, which is that of a mu-Galton-Watson tree. So the mu-Galton-Watson tree is a random tree where each node will draw its number of children independently at random according to the law mu. And with William Fleurat, we showed that there is an explicit law mu-u, which is in fact really simple, such that if mn is drawn according to PNU, then its tree of block is drawn according a law of mu-Galton-Watson, conditioned to be of size 2n. And this allows to give these results on a phase transition. So this is the case, again, of non-tree routine maps. We have a phase transition at u equals 9/5 with a subcritical phase, which is a general map phase, where we will find condensation, one huge block, a critical phase with a few large blocks, and a supercritical phase, which is a tree phase with only small blocks and generally tree-shaped maps. And in every case, we have explicit results on enumeration, size of blocks, and scaling limits. And the goal of my talk today is to explain how we can do the same for tree routine maps. So this is a joint work with Marie Albank and Eric Fusy. And we simply use the same Boltzmann model we had before, but now green P is a probability law for tree routine maps. U is to the power of the number of two connected tree routine blocks in the tree routine map. when u equals 1, it's simply the uniform distribution on tree-rooted maps. When u tends to 0, it's two connected tree-rooted maps which are favored, and when u tends to infinity, it's tree-rooted tree which are favored. And once again, the question is, given u, what is the asymptotic behavior of M drawn according to P and U when N tends to infinity? It sounds quite simple because, in fact, the decomposition of a map into a block tree extends readily to tree-rooted maps decomposed into tree-rooted blocks. And we have the same equation for the generating series of tree-rooted maps and two connected tree-rooted maps. Just beware that this B and this M are not the same as before. It's a generating series for tree-rooted maps and two connected tree-rooted maps. And we can add a weight U exactly as before. But unfortunately, even though it seems then that everything should be easy, it's not the case because the generating series are not as nice as the previous ones were. So we know the generating series, thanks to Malin, for tree-rooted maps. This gives the radius of convergence. Here you can notice that we have n to the power of -3, which is not the typical behavior of maps, which is n to the power of -5/2. This gives also the radius of convergence of the map. And when evaluating this series into its radius of convergence, we find a transcendental number, which shows that M is not an algebraic series. There is no polynomial relating M of Z, and Z, which was the case before for our M and B in the non-tree-rooted case. Unfortunately, M is still algebraic, is still definite, and we find a linear differential equation satisfied by M green. And that's the case for M, but B is really not so nice. So using the equation between M and B and the properties we have found for M, we can show that the radius of convergence of B is this transcendental number, which means that B is not definite. And B is what we call D-algebraic, and we find an explicit polynomial relating B and its derivatives. And this makes the studies quite more involved as before. Still, we managed to enumerate the number of two connected tree-rooted maps and show that it has this form. So notice the n to the power of -3, which is in fact the exponent which seems typical for tree-rooted maps. And this afterwards allows us to exhibit a phase transition for a UC which is now transcendental. And when n tends to infinity, we have a subcritical phase when U is less than UC, where we will have general tree-rooted map with, again, condensation, one huge block, a critical phase where is a few large blocks, and the supercritical phase, which is a tree phase with only small blocks. And more precisely, we can fill in this table. So for the enumeration, in the subcritical case, we have the n to the power of -3, which is typical for tree-rooted maps. In the supercritical case, we have n to the power of -3/2, which is typical for trees. And in the critical case, a new behavior emerges, which was the goal of the whole study, to make a new behavior emerge. So this is a success, with n to the power of -3/2 log n to the power of -1/2. For the size of the largest block, we show that we have, in the subcritical case, a macroscopic block with linear size, and the second block is of size square root of n. In the critical case, we have a few square root of n sized blocks, and in the supercritical case, our block are logarithmically sized. It's, in fact, a bit different from what we had in the non-tree-rooted case, because these two situations are defined by ordered atoms of a Poisson point process, which was not the case in the critical case for non-tree rooted maps. And as for scaling limits, in the subcritical case, we have no result because we did not try, because honestly, even for u equals 1, it's not known. So we had not really any hope of finding anything in the context of this study. In the supercritical case, it was already studied by Stuffler, who showed that there is convergence to the Brownian tree. And we show that in the critical case, there is also convergence towards the Brownian tree, but with a different rescaling. Here we have a square root of log n. And this, once again, is different from what happened in the non-tree rooted case, because in the non-tree rooted case, we do not have the same scaling limits in both cases. Here we have a stable tree. Now, what we hope to be doing in the future along these lines of work is extend this to more involved decompositions. For example, block-weighted tree-rooted quadrangulations, forested maps, maps endowed with a parts model or an Ising model, and two-oriented quadrangulation or tree-oriented triangulations decomposed into irreducible blocks. These decompositions are a bit more involved, not just a bit, they are more involved, but we hope that on the probabilistic level, this does not change too much, and that we'll be able to do the same kind of computations. Thank you very much.
Yeah, question specific. I have a weird historic question.
What do I hold on to? This?
If it's green, I think it's on.
Fine.
Don't press any buttons.
Oh, it's not on. Well, yeah, it is on when I talk. Early on, you had two references I noted. One was Mullen 67, and the other was Tutt's enumeration, probably a bit earlier.
Yes.
Were they both? Tutt's was on the number of planar maps.
Yes.
What was Mullen's on? Ron's on?
A tree-rooted planar maps.
Was which?
Tree-rooted planar maps.
Oh, also tree-rooted planar. I was wondering if they were coming from. Mullen was a student of Tutt around that time, maybe very slightly before. And I was wondering if they were coming from different sides of what you were looking at. But no, they're both the planar map thing. Fine. Thank you.
Thank you.
More questions?
Do you have any idea of what happened in the subcritical case?
Yes and no. So the physics give us an intuition as to the rescaling we should have for to get to the scaling limit. It should be around n to the powers of 0.27 or 0.28, but we don't even know which is the correct order of magnitude.